Hi there, and welcome to today's AWS webinar, Journey Through the Cloud. My name's Ryan, and I'm a technical evangelist at AWS, and I'm going to be your host for today's webinar. And today's webinar is entitled Powerful Web Applications, and specifically we're going to look at how you build such things in AWS. And the Journey webinar that we're going to take you through is really about looking at common use cases and common patterns that customers have used to deploy their applications into the cloud. And these form great stepping stones for you on your own journey, so you can learn from other customers' implementations and pick up some best practice to bootstrap your own projects. And when we talk about building powerful web applications, really this is about a common application type, the classic N-tier web application. And what we're going to do is summarize today some of the technical best practice from customer projects, binding together many of the use cases that we see and the technologies that we see in our customer base on what we consider a mainstay of many greenfield projects, that web application. And we're going to draw upon some of the technologies, some of the concepts that we've discussed in previous Journey webinars, and bind this together today in an agenda which looks at some of the drivers behind why we need to create powerful web applications, some of the business and technological pushes that drive us in a particular direction. And we're going to describe the rules, if you like, for how you build these applications and how you achieve architectural success. And we'll litter the webinar along the way with some customer examples. So without further ado, what do your users really want, and what causes us to think about building really powerful web applications? Well, users want a fast and performant experience. So it's very common knowledge, and there's many different research papers out there that will talk about the speed at which you respond to your customers will dictate how long they stay around. If you're slow, they will go. So responding very fast, being a generally consistent performing web application will keep your users happy and satisfy their need for a good on-demand, fast experience. And of course, that web application that they're accessing should always be on, and it should be accessible from anywhere. There shouldn't be any dead spots on where they're traveling, maybe with a mobile phone, and that application should always be available. There's nothing worse than coming to a website and finding that it's not available, or it's giving an HTTP 500 error or something similar. Modern users of web applications also look for highly personalized and rich applications. They expect, even after the first visit maybe to an application site, that their experience is customized, tailored to them, that the insight that a provider of that service has drawn from their interactions has driven the next stage of presentation of pages or suggestions to them on a site. So personalized and rich experiences are becoming the norm. And of course, users expect lots of new features all of the time. They expect things to be constantly innovating on behalf of them. They expect new, cool, fresh features to be delivered to them on a regular cycle, not waiting months or years to get refreshes of applications. In those cases, the application will seem stale, and those users tend to walk. So all of this brings us to a powerful web application. So satisfying those four needs is what I will try and describe a set of rules around for you today as a reference material, so that you can maybe take some of those rules and implement them in your own web applications. So how do we do that? Building powerful web applications, a rule book. So here are the rules, and I'm going to step through 6 main rules, and there'll be some sub-rules along the way as well. So rule 1 is about servicing all web requests. So it sounds obvious, but make sure requests can get to your front door. So if you think about how an application is built and how a general web request is served, the first thing we're going to get is a request that's going to query a DNS service to try and find an address for the application of where you're hosting from. That DNS will therefore point to your application. But if that DNS service isn't working and your clients can't resolve you, then it doesn't really matter the efforts that you put into scaling your application or making your data highly available becomes irrelevant, because simply the request won't find you. So making requests get to your front door in the context of AWS is all about the use of a service called Route 53. So Route 53 is our DNS service, and it's a globally provided service from all the edge locations that you may be familiar with, where we serve, for example, our CloudFront content from. It's a highly scalable service, and it's got some very nice features such as latency-based routing. It integrates with other services like CloudFront, S3 and EC2, and integrates with IAM. But the big thing about this is that it gives you a 100% available SLA. So if you check out the SLA at Route 53/SLA on the Amazon website, you'll see that we provide a response guarantee that we're going to respond to every request that comes at us. So in this way, you can be sure that if someone comes and tries to find your front door, the DNS service of Route 53 will direct you to the application where you're serving your content from. The next part of that is that when they do get to your front door, make sure that you open it when they arrive. So this is all about a standard HA, high availability, high performance architectural pattern that you'll find in many of our materials on our architectural best practice papers on our website. And it starts with the use of availability zones within a region and the use of elastic load balancing across instances in those availability zones. So shown here, I've actually got two regions, and in each region the pattern's the same. I have an elastic load balancer shown in blue, load balancing across 4 instances in orange, 2 in each availability zone, in this case within a region. So my application servers are spread across availability zones, which imply that they are in physically distinct facilities. And the load is load balanced by a regional service, the elastic load balancer. And by repeating that pattern in multiple regions around the world, I can achieve a global coverage and a very high availability application deployment that ensures that when people do come knocking on our front door, in this case our Route 53 directing to our elastic load balancers, that our application servers will be available to respond to that request. The next rule, Rule 1C, is of course most applications have some sort of data behind the scenes to drive the response that's formed to the user. So Rule 1C is have the data to form a response. So if we extend this pattern in the diagram below to include databases, then our best practice would look at us using something like relational database service for MySQL or Oracle or MS SQL. So the RDS wraps a database as a managed service, and it provides for things like MySQL and Oracle master-slave replication across multiple availability zones. And then across regions you can implement synchronization techniques so that you're synchronizing or sharding data across multiple regions in the world. And this way that you can be ensure that you have the data to form a response because you have a backbone or a data layer that is highly available. In the event of a problem, the relational database service will flip your DNS entry for the database endpoint and promote a slave to a master. So Rule 2, service requests as fast as possible. So part of this again falls back on Route 53. So one of the features of Route 53 is the ability for it to choose the fastest route to a given endpoint. So servicing requests as fast as possible in this case will mean going to a region where we're serving our application servers from that is closest. So as a request comes in, hits Route 53, Route 53 will choose the fastest route to that given user for forming a response. In this case, directing or returning a DNS entry for region A, which is giving the fastest response from Route 53 to the load balancer. So the DNS entry returned, well, in this case, could be, for example, Singapore if we're hosting in a Singapore region for somebody in Asia Pac. It could be Sydney if they're in Australia. So you can spread your application servers around regions in the globe and use Route 53 to ensure that wherever your users are, particularly if you have a global user base, you have the best possible response times for that user. Another rule, Rule 2B, is offload your application servers. Your application servers need to be doing the tasks that are most relevant to the application and nothing more. So any tasks that are wasting clock cycles on delivering, say, static content should be offloaded. And CloudFront is a way that you can front those application servers and distribute your content to edge locations for the best possible response. And at the same time, you will be offloading your application servers from performing those tasks, and therefore you can probably scale back those server clusters. So in this diagram here, I've got CloudFront fronting a load balancer, in this case fronting an auto-scaling group with some instances in it which are serving my dynamic content. So we can see served from EC2 is my PHP content, which is dynamically generated. Now CloudFront is also here serving static content, which I've stored in S3. So S3 being the simple storage service where I can store things with very high durability, a write once, read many web service. So ideal for hosting this sort of content. And we can see that CloudFront, I've put a rule there which is saying /images/star shall be served from an origin, in this case S3, whereas star PHP is served from my load balancer and my cluster within EC2. And then CloudFront will distribute that content to wherever my edge location users happen to be. So first request from somebody in London would make a request to the origin server, and then from that point forward, that POP in London would host the content locally, and therefore subsequent requests will get a very fast response. And the beauty of things like CloudFront is that you can front this with a single CNAME, such as mysite.com, and you can implement such a pattern with very low impact to your application behind the scenes with that sort of pattern. So looking at that a bit differently in terms of offloading the application load and therefore meeting our rule, which is to do things as fast as possible, so focusing our application servers on the tasks that they need to be doing, generating dynamic content. Without CloudFront, we might have a cluster of 6 instances, and they may be under load and firing off CPU utilization requests or alarms through something like CloudWatch. With CloudFront, we can offload some of that processing and the serving of that web content onto CloudFront, and we'll be using an optimized network between CloudFront edge locations and EC2, and we can scale down the number of servers that we're using to serve the response. So here RDS, and I've got my app servers on top. I've reduced from 6 to 3, and I've introduced S3 and CloudFront into the mix. So all in all, I can generally improve the performance of my response time, and I can offload server load and therefore reduce some costs. So a comparative chart with no CDN, I would have a response time that's high and a server load that's high. I can then use CDN for my static content only and get a series of gains. But with CloudFront, I can also front dynamic content and have very, very low TTLs, or even TTLs of 0 on dynamic pages, and simply leverage the optimized TCP network between edge and backend servers, and offload some of the TCP creation and teardown that will result in a lower utilization on CPU on the servers behind the scenes. Another thing, rule 2C, is cache it if you can. So you can be in a situation where you're scaling databases to a very high level in order to handle the request rate that's hitting them. If you find yourself in those situations, you want to serve commonly or frequently requested and slow changing data from a scalable cache, and in this case a memcached managed framework called Elasticache. So shown in the diagram here, I fronted my RDS master and slave with an in-memory cache built on Elasticache that's spread across availability zones, and here I've got automatically created 4 instances in each availability zone that's going to front commonly accessed content, and therefore I can reduce the load on the database server and improve the overall performance of my application, because I'm going to get a much faster hit from Elasticache than I will from a database. So cache it if you can. Rule 2D is around the performance of databases and the latency that we may get from requests that we can't cache. So shown here is a chart where I have database query performance versus scale. And with a relational database, or any database, our desired consistency and predictability on performance is the straight line I've shown there. So regardless of the scale of my data or the database that I'm operating at, I want to get a consistent database query performance so that I can predict how my application will perform for end users. But what actually happens is as I scale my database, as my data sets get larger, the number of records in my database grows, the indexes grow around that, I actually get degraded performance with scale. And the challenges that we have in terms of bridging that gap are things like how do we shard our databases, implementing data caching where we can, the provisioning of multiple clusters of databases and the management of those clusters, and the fault management or the fault diagnosis when something goes wrong. It becomes an increasingly difficult operations task to manage large-scale relational databases. And this is where DynamoDB comes in. So DynamoDB is our managed NoSQL data store that gives consistent low latency at very large scales with zero admin, so predictable performance and single-digit latencies for certain data structures. So it's a NoSQL store, so essentially a key value store, non-relational, so you have to think differently about your data models. But where you have hotspots in your data structures, you can consider using a Dynamo table because you can provision the amount of throughput that you require. So it could be that you start off with 5 reads writes per second, and we will provision the right hardware behind the scenes and shard your data across a Dynamo service running on SSD drives to maintain the desired throughput. If you then want 100 read writes per second, 1,000, 10,000, you can simply dial up the capacity and pay for that provisioned throughput, and we will do all the work of managing the cluster behind the scenes, delivering average single-digit millisecond server-side latencies. So you can be sure that for those hotspots on your data structures that are getting hit a lot and are very latency sensitive, that your end users won't feel the impact of a degrading performance on a relational structure. Okay, so that's rule 1 and 2. Rule 3 is handle requests at any scale. So we've managed to serve the requests. We're serving them as fast as possible when they hit us. Now, scale starts to come, many hundreds of thousands of users. We need to handle them at any scale. So rule 3A is scale up. So this is a way that you can buy a lot of time in your architectures, starting with small instances and then simply choosing a larger instance as the need dictates. So there's a whole range of instance types that you can choose from, and indeed there's more than my slide is already out of date, because we have new second generation class of instances being released in the US, soon to come to Europe, where we have changing the ratios between CPU and memory, and you can even choose instances backed with SSD drives on the local ephemeral storage. So scale up on EC2 instances. Of course you can scale out. So where your architecture enables you to do so, we would encourage you to scale out, because you can take advantage of things like auto-scaling. So auto-scaling is the ability for the servers behind a particular workload to expand in number or contract based upon the demand being placed upon that cluster. So shown here is an auto-scaling group that has a minimum size of 4 that could expand to a maximum size of 200 based upon some sort of trigger. And the triggers can be varying. So they could be based upon alarm metrics from CloudWatch, they could be custom metrics written for your application, or they could be by schedule, for example. So scaling out by auto-scaling, you could initiate a simple CLI call and set the desired capacity of your cluster. So maybe you see from your monitoring frameworks that your load is increasing and you want to add 20% more capacity to your server pool. A single CLI command will do that. You could have a schedule that every Friday night your application is heavily loaded and on a Saturday morning it's not. So you could double your capacity on a Friday lunchtime and then halve your capacity on a Saturday morning, for example. Or by policy, and this is the dynamic aspect of auto-scaling. So this is responding to changing conditions. So following, say, CloudWatch metrics, maybe average CPU across a cluster. Or it could be latency as seen from an elastic load balancer. As that starts to degrade, add more servers to the cluster to perform the particular task in hand. And auto-scaling also feeds into high availability, because auto-scaling works across availability zones. It can rebalance the number of servers that you have in any availability zone to ensure that you have an even spread of capacity. So how that works is that if an availability zone has a problem, let's say I had 10 servers across 2 availability zones, auto-balancing will ensure that 10 servers exist in this remaining single availability zone by starting 5 new ones in that availability zone. And when availability zones come back up and I have 2 available to me again, auto-scaling will rebalance and put 5 in each for you. So it will always ensure that you have the right capacity, but always ensure that it's balanced as well as possible across availability zones for HA. So examples: preemptive scaling, which I've discussed, regular scaling on schedule, dynamic scaling, SQS queue depth, for example, average CPU load, ELB latency, and of course the auto rebalancing that I've just mentioned. Another aspect of scaling in AWS is the ability to dial up capacity. So I mentioned DynamoDB being able to provision a certain capacity behind a table by selecting a desired rate that you might wish to achieve. And behind the scenes, we will go and provision the right amount of hardware and do the right amount of sharding to ensure that you can achieve that. Provisioned capacity is about dialing it up. So a simple knob which you can tune to give you the capacity you require. And you will pay for that capacity regardless of whether you use it or not. So different from maybe scaling up, where you only pay for the instances that are being run at any particular time. And you're not paying for the maximum amount of an auto-scaling group, for example. Provision capacity gives you the ability and the comfort to set a level that you wish something to perform at. And that extends also to the Elastic Block Store, which is the volumes behind EC2 instances and behind relational database service. So if you have particular intensive workloads that require consistency in the provisioned I/O against disk volumes, you can provision IOPS on a volume, and then you can stripe those volumes and achieve very high I/O rates against EBS block stores. So Shazam is a customer example, so popular music recognition and tagging site. So during the Super Bowl, they talked about using DynamoDB to handle unprecedented demand. And DynamoDB operated at over 500,000 writes per second. And they also drove an EMR cluster, an Elastic MapReduce, which we'll talk about later in this webinar, to more than 1 million writes per second. So capacity that they couldn't have brought online with a traditional facility, they were simply able to dial up and then have that capacity available to them a few minutes later once the scale out operation had completed and their table was provisioned at the new levels that they required. So a huge amount of capacity brought on tap, which they could dial back down again once the demand went past. So truly high scale NoSQL database. So rules 1, 2 and 3 really dealt with fundamentals of architecture and how to ensure that we service requests when they hit us, how to do that as fast as possible and to do that at any scale. Rule 4 moves us into more subtle architectural patterns and methods which lead upon our last journey of the webinar service, which is simplifying architecture with services. So rather than installing things and managing those and therefore spending a lot of time managing what we'd call undifferentiated heavy lifting, such as installing middleware software into your application server environments, managing those, ensuring those scale, you can flip that ratio of 70-30 to spending more time on your business by letting the cloud provider, in this case AWS, take on the management of common infrastructure from compute, but also to software, so that you can actually spend time configuring cloud assets as opposed to doing all the fundamental undifferentiated heavy lifting of installing, managing, monitoring those frameworks. So more time focusing on your business or your application by simplifying your architecture through the use of services rather than installing and running software. So some of those services that I've mentioned already are relational database service and DynamoDB. So rather than install a database on an EC2 instance, deal with the backups, the snapshotting of that database, deal with the high availability clustering and the monitoring for event of failover, you can simply use database as a service. So choose to start an instance of a particular size, running a particular database platform version, and tick the box to say HA, and tick the box to say I'll have 35 days worth of backup history, please. And we'll take care of all the management of that database for you and just provide you with an endpoint that you can consume in your apps. Likewise, DynamoDB takes away the management of large-scale clusters for NoSQL stores. So whereas you might be installing a Cassandra or Mongo cluster, and you're going to have to scale that cluster, manage many instances in the cloud for dealing with running that database, DynamoDB simply gives you a simple interface with desired throughput capacity and will take care of the fully distributed nature of that cluster, the fault-tolerant architecture, the resharding and management of the performance of those indexes to give you consistent throughput. But there are other services that can really help you simplify architecture, improve overall reliability and availability too, because services such as SQS operate fundamentally at a regional level. So SQS is a queuing service, and queues are very common for decoupling application components in your applications, ability for you to deposit a message in a queue and have that read at some other point in time, and have that queue reliably hold that message for you, such that if endpoints go down, the queue persists and things can be restarted. So a queue becomes a fundamental reliable store of a critical piece of transactional information in many applications, so that queue needs to be highly available and reliable. So rather than you install clusters as a service to manage queues, you can use Amazon SQS and at a very low price point achieve the same sort of reliability as you achieve with S3 for your messages that are passing between application nodes. So highly reliable, regional level message store, and you simply put and get messages from the queues. Simple workflow expands upon that. So rather than maybe just doing simple step processes where we deposit a message from one application to another via a queue, we might want to control decisions such as the content of that message might drive moving to application A or B to do particularly different jobs as part of a workflow. And simple workflow enables you to take all the processing state out of your application endpoints and put them again into a regional service that's highly reliable so that state persists for long-running transactions. And you implement a simple decider process which will decide what tasks should be done when under what conditions. So simple process logic defined in your favorite programming language, as opposed to something like BPML, which is sophisticated, hard to understand and complicated. Other services, cloud search replaces the need for you to install maybe an open search framework in the cloud. So this is built upon the Amazon A9 search engine, and you can simply start a search domain, upload some documents to an endpoint and have them indexed in the way that you choose, and then you search against an endpoint and get some JSON results. And this again is an elastic service that grows as the demand for searches increases. So you can get consistent performance out of search. So search, a very common use case in many web applications. But at the back end of applications, we also have the need to do some analysis. And with powerful web applications, with many users and many transactions hitting us at a time, we can generate very, very large click logs or application logs out the back end of them. And gaining insight into those can be tricky in a timely fashion. And Elastic MapReduce is a service that wraps Hadoop, the framework for doing large-scale parallel operations on datasets. And we'll talk about Hadoop a bit later on. So SmugMug is an example of a company that uses cloud search and uses cloud search fundamentally to drive their image sharing applications. So it's a game-changing technology. Their CEO and chief geek talks about it, about them saving many months of re-architecture and development time by going with cloud search with its simple endpoints, as opposed to managing and installing an open search cluster in their environment. Everyone knows what a search box looks like, so this is SmugMug searching for Paris. And here we can see results for images from Paris. And just like if you went to Amazon retail site, you would see search results with facets and categories. Here my facets on photographs are the apertures, and the number of photos with different aperture settings can be seen there. And you can achieve similar sort of faceting and grouping of documents for a simple web interface for cloud search. Okay, so we've simplified our architecture. So rather than installing pieces of software and managing the availability, reliability and scale of those pieces of software, we've pushed common tasks into cloud services and consumed them on the same basis as we might consume an EC2 instance. The next rule for really powerful applications is where we start getting sophisticated around the operational management of the application. So automate operational management. And everything is programmable. So within AWS, everything is wrapped as a nice web service API, and those APIs are wrapped via CLI, command line interfaces. Your favorite programming language APIs will expose them, SDKs, and indeed our console is built upon those same APIs, so you can access everything programmatically, and you can therefore achieve sophisticated levels of automation with relative ease, whether it be in your favorite scripting language or your favorite programming language. You can consider the AWS resource set as transient and as accessible as instantiating an object in your code. So when you need a server, you can create one programmatically. When you're done with it, you can destroy it programmatically. And that drives a number of philosophical changes in how you consider compute and architectures. And first of those is that you should think disposable, if you like, one-click deployments. So building upon that ability to automate everything is a framework called CloudFormation. And I've drawn this out in this rule because CloudFormation lets you specify a complex set of resources that can be created in a transactional way. So it might be that you create a CloudFormation template, which is a load balancer with a series of application servers behind it, caching servers, and some DNS registrations. And this could be a unit of scaling in a very complicated application. And that CloudFormation template, you could choose then to deploy that set of components in a region and an availability zone around the world on demand, on a click, or via a programmatic call. And when you're done with it, you can throw that stack away and all those resources get taken back. And this is indeed the way that many customers deploy very sophisticated units of scaling beyond a simple server. They can be many hundreds of servers in a single stack. And when they're done with it, they can dispose of it. So think disposable one-click deployments. And CloudFormation is a great tool for you to achieve that. Next sort of rule around operational management is design for failure and implement self-healing. So there's a number of techniques that you should consider to enable you to design and understand and accommodate failures, but also to recover from them when they happen. So bootstrapping your instances is the first kind of part of this. So when an instance starts up, get that instance to ask, who am I? What should I be doing? What's my role within this architecture? And then get that instance to be configured dynamically upon receiving the answer to that question. And you can achieve this through the metadata service within AWS with bootstrapping scripts that you install and bake into an AMI, and for maybe pulling configuration files or application content from S3. And classically, this is what we call bootstrapping. Another part of designing for failure is using the minimum pool size of autoscaling. So even if this is one server, put in an auto-scaling group of minimum 1, maximum 1. Then if any health check fails from an EC2 perspective on that instance, auto-scaling will take that out of the pool and will replace it based upon the auto-scaling configuration. So it could just be a simple like-for-like replacement to ensure that you always have a minimum set of capacity available. So automatically restarting or creating new resources, throwing the old one away, adding a new fresh one. And then CloudWatch is your monitoring framework to enable you to know what's going on and then to drive those automated actions. So auto-scaling could respond to it. You could take actions to initiate CloudFormation scripts and various different sophistications, even getting into the worlds of Chef and Puppets as frameworks that you might install on instances to drive cookbooks and recipes. And a very commonly talked about example nowadays is the Netflix Chaos Monkey. That Netflix really take those principles to the extreme in that they have an open source software agent which they've released called Chaos Monkey that essentially runs around their environment and causes havoc, pulls things apart, stops instances, destroys processes, takes databases out, and it engenders a design philosophy in anyone that's writing application code for Netflix to think that that monkey could be running across your code and turning it off at some point. So they need to think about when service owners deploy parts of the Netflix framework is how will my service respond in the event of a failure or a degraded performance? And they're designing from that up front such that the overall global architecture of Netflix is highly fault tolerant and can survive failures which happen all the time at very large scale. Statistically, if something will happen once in a million, if you're operating at a significantly higher scale web application, it will happen more often than not. Lastly, rule 6 is about leveraging some unique properties of the cloud. So cloud brings some fresh things to the game that we can leverage to make our architectures more powerful and also to drive that satisfaction cycle back to our users. So optimizing costs is one of the things. You can choose different instances to get different jobs done. So think about the density of compute you can get out of a particular instance type to drive a particular workload. So you might consider cluster computes to do encoding of videos versus you might just use the standard medium instances to deliver a fleet of web servers to handle a particular task. And there's different instance families, and shown here is a selection of them from high memories, might be good for caching servers. So mix and match the different instance types to drive a particular type of workload. But also, those instance types can be acquired in different ways. So classic on-demand computing starts at 2 cents an hour, which is a pay-as-you-go price for a Linux instance. You grab it, you pay for that per hour, and when you're done with it, you stop paying. So great flexibility around the consumption of compute. But many servers, base level servers within an environment, will be running all the time and expected to be on 24/7. In this case, you can reduce costs by reserving that capacity. So a billing mechanism in AWS allows you to purchase a reserved instance on a 1 or 3 year term. So you pay a little bit up front, but then you receive a significant hourly discount. So you can achieve some fantastic ROIs by doing this. And this is a billing mechanism that layers when you're running a server of that particular type, you will receive that discount. And then on the far right there, we have spot instances. So this is the ability for you to bid on unused EC2 capacity, whose price for that capacity varies based upon the supply and demand being put on that particular instance type. So great for use cases where you have flexibility in when you might get the instances for requirement, or that are only feasible at a different economic rate. So might be very large scale load testing. You want thousands of small instances to hit your website to simulate some user load. You can achieve that with spot instances at a much reduced price. So a way of layering these instance types: reserved instances for things that are always running, on demand for the middle section of variability, and then for exceptional cases that might not happen that often, use spot to soak up that extra demand load. I mentioned earlier Elastic MapReduce, and Elastic MapReduce really allows you to drive upon those cost equations and achieve analysis that isn't feasible within a sort of normal classic fixed cluster size that you might have in your traditional data centers. So Elastic MapReduce is the ability for you to split a computational task across many nodes, many instances, and then aggregate the results back together afterwards to give you some sort of insight. And it scales on a pretty much linear basis. So the more instances I add to a MapReduce cluster, the quicker I get the job done. And if you think about having S3 as a source of data, such as click log analysis. So if you think about understanding what people have done on your web application by interrogating the logs, you might have terabytes of log that you wish to analyze. That's only feasible if you can apply a significant amount of horsepower to maybe do a simple computational counting task or sum task across those very large log files, in which case you can deposit the logs into something like S3. You can write a very simple piece of code in your favorite language and drop that into Elastic MapReduce. And Elastic MapReduce will then go and create a cluster with a distributed file system behind it that will enable you to run that task across pieces of the data. So we'll pull the data in, spread it across many instances, and then afterwards we'll aggregate the results and output it back into, say, S3. But you can also then query that distributed data set across the distributed file system. And when the job's done, that whole cluster will be destroyed. Now, think about the cost dynamic. Because it scales linearly, I might have 4 instances assigned to a job. And that duration, let's say, takes 14 hours to do a particular task. And that cost, let's say we're using an instance on demand, 4 instances at 40 hours. And let's say, for the sake of argument, that instance cost me 50 cents. It will cost me $28 to run that job over 14 hours. Now, if I add 5 spot instances to that, because I'm near linear here, I'm kind of doubling the capacity that I have behind this job. I can expect the duration to take half as long. So they're about 7 hours instead. Now the costs of this would be my existing price of on demand, but for half the time. So 4 instances at 7 hours at 50 cents is $14. And then my spot, let's assume that my spot price is half the on demand price. And quite often it's significantly less than that. So you can get far greater savings on the spot market. For example, I think the last time I looked at cluster computes were $2.79 on demand and 56 cents on the spot market. So significant savings. But in this example, adding spot instances at that half price gives me a total price of $22.75. and I get the job done in half the time. So I've paid less and I've got it done quicker. Okay, so very unique property of cloud, and in particular when we start thinking about parallelization of jobs. Now this enables you to analyze very large data sets in a time frame that's feasible to actually do something with them. So Yelp is a popular city-based yellow pages that's coming to Europe quite significantly at the moment. It's growing in size. They run about 200 of these elastic MapReduce jobs per day, processing 3 terabytes of data that's kicking out of their web application servers. So just dragging those logs into an EMR, running continual cycles on the jobs to generate content which sits behind their app servers. So generating lists, things like autocomplete lists as people type on the search boxes, spelling suggestions in those search boxes, taking review highlight snippets and generating them into static content to drive their web app, doing analysis about who viewed what, also viewed this, so they can generate those suggestions to users, and also looking at things like top searches and driving the adverts to place. Okay, so fundamental to driving a very dynamic application by taking these log files, churning them with significant compute capacity to get them done in a time that makes sense to drop them back into the app to make things feel very dynamic. Another thing that you can get with the cloud is that you can get a supercomputer backend when you need it. And drawing upon that, the idea with Elastic MapReduce, you could have thousands of nodes in Elastic MapReduce cluster. If you need to do some very computationally intensive tasks, you can also generate highly interconnected algorithms that run across the supercomputer backend. Because our cluster compute instances operate in network placement groups, so that means that every node has full 10 gig full bisected network access to every other node, so they can pass messages between each other with ease and very low latency. And each of these nodes can be significant in size, so 60 gig of RAM, 80 EC2 compute units. So you can run big compute tasks on EC2, and then when you're done with doing that, you can throw them away. So common use cases for this might be rendering, image rendering, visualizations, encodings, and so on, as well as scientific research. Okay, so these are my rules. Rules 1 through to 6, servicing all requests, making sure that I serve them as fast as possible at any scale. Simplifying my architecture for the use of services, not installing and managing my own software. Automating everything so that I can run this thing from my iPhone on the way home from work, and then to leverage some unique cloud properties to drive insights and some unique things from a cost perspective and a performance perspective by using cloud services. So circling back to what your users want, they want a fast performant experience. Get that through elastic utility and capacity on demand from AWS. They want an always-on, accessible anywhere experience, highly available global coverage, regions, availability zones, architectural best practice, auto-scaling to do balancing across AZs. They want lots of new features all of the time, so the ability to do highly agile operations and automate things like the rollout of new application versions on a consistent and continual basis with AWS automation, and personalized and rich web application experience, cost-effective storage of vast amounts of data that then can drive big data analytics with things like Hadoop or cluster compute instances to drive the insight to give that highly personalized experience from a user, even after very few interactions with your web applications. So that's the rule book that I wanted to deliver today. Hopefully you found that of value, and it certainly covers most of the questions that people will ask us in various levels of how do I achieve this or how should I do that. So it gives you some best practice and drops some application services in the mix for you to consider. If you want to think about how all of those concepts are applied, there's a great example of NASA TV. So NASA TV use Route 53 to globally distribute content across the world. They're using multi-regions and multi-availability zones. They're using elastic load balancing across multiple instances. They're using CloudFront to offload content for delivering media, and they're using CloudFormation to deliver big sophisticated stacks, which they're units of scaling. So they encompass all of these things together, and it's an interesting example. It's not your classic web application, but it's streaming media and many eyeballs on the new content that comes back from the Curiosity rover from Mars. So if you want to find out more, do go to our aws.amazon.com website. You can obviously sign up to a free tier. and you can consume a lot of those services that I've discussed and have a play with them within that free tier. You'll find architectural best practice white papers up there, and also you'll find our next events. So we have a webinar on cost optimization as our last in the Journey series. But if you're looking for previous webinars, you can search our YouTube channel. If you search for the Journey Through the Cloud series, you'll find all of these webinars, all recorded for you to watch on demand. So thank you very much for joining us today. I hope you found it useful, and hopefully we'll meet any of you next week on our next webinar.